Our next speaker is also a future member of the faculty here, actually starting in about a couple months.
Yeah.
So Pengjie Wang will talk about blender liquids.
Okay, thank you everyone. It's my great honor to come here to present our recent results. And we are struggle to name this phase which we observe. And so we now name it as a two-dimensional anisotropic Luttinger liquid. But as you know, the Luttinger liquid usually will refer to the one-dimensional situation. So we are a little bit struggling it, but we call it in this name, and I hope that you understand after my talk what I'm talking about. So first of all, I want to acknowledge the group member. I was doing my postdoc. I'm doing my postdoc with Professor Sanfeng Wu, and this project was led by his supervision, and I strongly in collaboration with Guoyu, who majorly work on this project. And we got nicely crystal from Leslie Shu Bokava and HBN crystal from the Japanese group. And we also have theoretical support and calculation about the Moiré lattice from Sid and Shivaji and their students. And also we are really acknowledge the founders which make this project possible. So first of all, I want to show a picture which was in 2019 and February 28th. It was just 2 months after I arrived at Princeton doing my postdoc, when Tony went there for a public lecture, and I was really excited. I went there because it's just next to the physics building. And as you can see, it's really crowded of people. I cannot even find a seat over there. And this is what I'm going to talk later. I will mention you why it's different. First of all, as you know that for Fermi liquids, it's a kind of standard description for the metals in 2 dimensions and 3 dimensions. And we now know from Fermi liquid theory to quantum Hall effect and superconductivity, as it shows for the energy dispersion. And we can imagine that the Fermi liquid, we can simplify it, like renormalize it to a free electron, but it's in a kind of loose space, and the electron can be renormalized with effective mass, and it can move like a single free electrons. But the different case for we so-called it non-Fermi liquid is a case that we don't know. So for example, if you have a fish in the ocean and then you have a turtle, we don't know how to name them, then we call it non-fish. And maybe in the future, sometime we know, oh, this kind of category, we call it turtle. The other category, we call it lobster, which we add yesterday, sorry. But, it's something that we don't know. We try to give them another name, and later on we try to name them something that we know specifically. So an example, very good example, is that the 1D Luttinger liquid. So if you have a 1-dimension system and the electron can only move forward and backward in the 1D situation, and then the electron will be strongly confined. And the situation can be in analogy to another situation that when we were waiting in a line, and if you want to cut in a line, and then people will kick you out because they don't want you to cut. But this situation, I think it may be a little bit different for Tony, because when Tony was there, probably it will become 2-dimension, because everyone will come to Tony, say, hey, Tony, how you get Nobel Prize? But I know Tony doesn't like this question. And so in this situation, so even weak interaction in 2 dimensions, in 1 dimension, can strongly lead to the strong correlations. And also, they show a very different spectrum in the momentum space. And as a consequence of such a 1-dimensional Luttinger liquid, the density of state will be parallel to the energy. And this is a very important result which comes from the Luttinger liquids. And such a strong correlation, it can also lead to a collective excitation, so which is the spin-charge separation. So the spin and the charge can be effectively separate on the space. And moreover, this kind of model is exactly solvable. It has been pioneered by many series in the past 50 years. And experimentally, it's also exciting that we can realize them in many, many different systems. For example, nanowire, the engineered quantum wires, topological edges, and also cosy one-dimensional organic systems, and also self-organized wires. And as we mentioned, that this kind of parallel density of state, it actually can be converted to two situations of energy. For example, the external bias excitation, and also the temperature thermal fluctuation. And so for these two situations, they should both follow the parallel alpha. And if this is a Luttinger liquid, the alpha should be the equal number for these two situations. And a direct result that you can do a parallel scaling and in the transport measurement, so which you can correspond to the alpha number here, and they should be all the same. And experimentally, if we examine a system, if it is a Luttinger liquid, and we should expect that at low temperature region, it shows a temperature parallel. But when it is a high bias region, it shows a external bias parallel. And the question is that whether we can extend such a one-dimensional Luttinger liquid to a two-dimensional situation. And this was first proposed by Phil Anderson, trying to understand the cuprate system. But later on, it has been extensively studied and finished by many of you guys here and our pioneers, a lot of them here. And so this is the question is that in such a coupled wire system, and if you have an electron sitting in each independent wire, and if they have some coupling in between, and what's the situation at a very low temperature, and what kind of phase is going to behave? A simple understanding is that everything will get correlated, and electron interaction will lead to a two-dimensional situation or gap state. And is it possible that we really push down this T star, or like this so-called crossover temperature, down to 0? And this is a very interesting question proposed. And actually, theoretically, they have proposed this kind of phase diagram, which the kappa 1 is the inter-wire coupling, and the kappa 0 is the intra-wire coupling. And they found a phase here, which requires a really fine tune for the inter-wire coupling and also intra-wire coupling. And here is the phase which they name it symmetric metal or sliding Luttinger liquids. And in this phase, it shows up strong anisotropy, parallel behavior, and also it has a very strong inter-wire coupling. And it is also a kind of two-dimensional anisotropic Luttinger liquids. But experimentally, if you want to realize such a system, for example, if you want to lay a lot of one-dimensional wire in parallel to each other with a specific distance, it's really challenging. Today, I want to show you one example that may be possible toward this direction. So this is the twisted tungsten diterite system. It can be created by the Moiré lattice and then getting a very highly crystalline quality together with the highly tunability. So let me start with the Moiré tungsten diterite. So Moiré tungsten diterite, it has a rectangular lattice, which shows like this. And then the tungsten actually shows the zigzag chain like here. So you can see here. And it shows like a 1D stripes. And this system has been observed many interesting phenomena. For example, the quantum spin Hall insulator, external insulator, and also tunable superconductor at the highly doping region. And in an XTM study recently, we collaborate with Adi Yastani. We can find that the topography of the conductance of the tunneling current actually shows a stripes. And this is because the tungsten atom, the tellurium atom gets pushed up like this. And if you twist it, this is the situation that we are going to see. And I'm going to show you the Moiré lattice that it looks like. So this is a tungsten diterite, and then we twist it by some angle. Sorry, the animation is not so good, but if you okay, so if you look here, the Moiré seems like here it shows the unit cell is still the rectangular, but it shows also kind of stripe feature like this. And if I remove all the tellurium atoms, you are going to see that it shows out like a 1D stripe in this way. And experimentally, also like theoretically, you can calculate the distance between the wire, and then you can engineer your twist angle and to reach whichever number that you want to get. The long width and the short width is around 1/2, so it's around 2. Yeah. And so experimentally, we can actually visualize it. For example, we can do conductive AFM. We image the Moiré, and this is a real imaging of the Moiré superlattice. You can see the interchanging stripes. You can see the local conductance to be high and low interchanging. And the distance also overlaps very well with the calculation. And you can also do TM. This is a result which we recently collaborated with Leslie Shoup's group in Princeton. And we can do the TM imaging, and also with 5-degree twist angle, it goes to around 0.3 nanometer Moiré distance. It can also show the very nicely interchanging like wires. Yes, so this is actually, I call it AB overlapping, so which is the most less overlap region. But we didn't see any lattice construction in this large twist angle. If you go to much lower, it may be a lot of like lattice reconstruction. And so let's move forward to the anisotropy measurement or the electrical transform measurement. So this measurement was done possible with this kind of design, which we can only touch to the bulk of the twist area. The reason is because this monolayer tungsten diterite, it is edge conducting, and the typical method is going to touch the edge and also the monolayer area is going to confuse your measurement. So all our measurement, we only touch to the twist area as a contact, and then we can measure either the anisotropy or transport property of the material. So first result shows you we measure along different kind of orientation. And actually, we keep changing the contact configuration. We do a rotation, and this is the selected result, which I show you to show the distinct difference along two orthogonal orientation. And it didn't show very clear for the stripe which I plot here, but the stripe on this plot should be goes like this way, and the stripe in this plot also goes like this way. And so which means that when we send the current along this direction, it shows dramatically high resistance. And when we send the current along the orthogonal orientation, it shows like a very low resistance. And this also can be verified by plotting it as a log plot, because here is not 0, it's actually around a kilo ohm. And we can verify this characteristic with, sorry? Which one? Sorry. It's the density. It's the doping density. We get it. So we actually have a 2 gating. Sorry, I forgot to mention. We actually have a 2 gating. So we can actually tune the density as well as the displacement field. But in this measurement I show you is only focused on the density tunable. And the displacement field usually is 0. And so in this anisotropy plot, you can see that the anisotropy of this measurement can go to around 1,000. But I want to note that it's not meaning that the resistivity is 1,000, because there is a geometry factor, and the resistivity is around 50. Resistivity anisotropy is around 50. So along the hard orientation over the easy orientation is around 50 for resistivity. And we can reproduce in 5 degree, we can reproduce in 6 degree. And we can all, yes. Yeah, the resistivity. But the lattice difference is like 1/2. So yeah. And for the 2D plot, which we actually have a top gate and also the bottom gating, so which we can tune the full phase. Along this direction is the density doping, along this direction is the displacement doping. You can see on the left bottom side, it shows a very highly anisotropy, and the right top side it shows a much less anisotropy. So it's actually isotropic. And you can from here you can know that in the whole dope region, it actually shows a very highly anisotropy feature. And we keep going, we can identify and characterize this anisotropy with temperature dependence, just to confirm that it's not coming out from like a disorder, or we didn't twist it in a very good fashion, or there is a strain on the system. And we can characterize this by, first of all, you can check the anisotropy ratio decrease with increasing the temperature. And the second is that it shows a completely contrast different behavior along the hard direction and easy direction. So along the hard direction, actually the resistance shoots up with decreasing the temperature. But along the easy direction, the resistance actually goes up and then comes back down like a metal at low temperature. So we focus on a gating, which we park here, and then I'm going to show you more data, which we put the gate at other spots. And then we perform the measurement, which we do across the wire and two-probe measurement. And this measurement allow us to send to bias the sample, and also add an additional bias, so measuring the differential conductance and then versus the external bias. And you can first check the zero bias conductance. As you can see here, we plot it to a dual log plot. And the conductance versus the temperature actually shows the power law to be 1, around 1. For 6 degree, for 5 degree, it shows around 1. For 6 degree, it shows 1.14. And on the external bias measurement, as you can see from the left plot is the original data. And then on the right is which we scale to a single number for the data here, which we use the 0.98 power law we extract from here. And as you can see, all the data set, it actually collapsed all together here. And one more point that I want to point out, distinct from most of the previous results, for example, in the carbon nanotube or in the fraction quantum H modes for the tunneling, is that if you just cross this line here and this low bias line here, and then you get a crossing point somewhere here, which means that the EV over KBT, the energy scale number here is not unitary. It's actually some number between 10 to 100, or I would say if we extract here, it's around like 30, 40. And actually, I think it indicates some number which how many wire tunneling process you might have in between this system. If you simply suggest it is a single wire system and then it keeps tunneling between wire to wire, and then you might anticipate some number that how many tunneling process to be equivalent to each other and keep tunneling to the next contact. So in this situation, actually suggests you have around 30 equivalent tunneling process. And in our measurement, the distance, yeah, yes. So for this kind of situation, if you measure, if you calculate how many wire you might have in such a Moiré system, the number is around 70. So it's around a half. So which means that you still have some disorder. You still have some other component which may be shorting the measurement. But the dominating factor is that you have 30 equivalent tunneling process along this geometry measurement. And what is more is that we need to be careful here because so in some early theoretical or like measurement, people usually claim like saying they are Luttinger-Liquid, but they might have different kind of power law number, and which might be induced by disorder. But here, I want to address that in our measurement, the power law number here is always a single alpha. And this alpha can be extracted either by temperature dependence or the external bias. And so I want to conclude here, say we have a power law conductance in the hard orientation. And the next, I want to show you the early apparent or like the explanation that it might be trivial coming from like the variable hopping or other mechanism, and they propose it might also show a power law-like behavior. But in all this paper, and it was summarized by Sasha Fogler, and as you can see that in the prediction and also in this theoretical paper, in general, the alpha will be different from beta, which is the power law at the temperature dependence and the power law at the external bias. But in our situation, the alpha is always the same as the so-called beta. So the temperature dependence and the external bias dependence are always has the same Luttinger-Liquid number or the power law number. And so we think that it's unlikely to be feasible for here to really reach such a like alpha equal to beta, but this is what the case it is in our system. And we can keep changing the gating, just like changing the disorder density or changing the system's density. We can keep seeing this kind of alpha equals to beta is always there. And this is the data. This is the first device at 5 degrees. We extract many data points. I pick 3 here to show you the example that it always shows very good overlap of the alpha. If we just take the alpha, the number from the temperature dependence is always here. And it can always collapse very well with the scaling. And the 6 degree is the same, that we can keep getting the same alpha equals to beta. And so I want to address that here is that in our situation of this scaling, the alpha is always equals to beta, which means that at the temperature power law and the external bias power law, they always share the same power law number. And we also can confirm this with more devices. For example, we have another device. We have another 2, actually more than 2 devices at around 3 degrees. For 3 degrees, it will actually increase a little bit of the Moiré lattice size. And in this situation, we can still measure and we can still getting the power law relation down to 50 millikelvin for this power law behavior. And we can reproducibly getting the anisotropy. We can getting the power law scaling. And one more point that I want to talk about is that for this measurement, like the anisotropic measurement, if you measure along the so-called easy direction, it actually shows something similar, looks like a superconductivity. But it is obviously not a superconductivity because in our measurement, when we apply a magnetic field, we cannot kill this superconductivity. It's still there. And along another direction, it also shows a really strong contrast versus this easy direction. It shows a very, very high resistance. With external bias, you can just suppress it down. If you check the anisotropy, which is this number over this number, you can see that the anisotropy in this 3 degree device, it can go to even higher at very low temperature, say 50 millikelvin in this situation. You can go to 10 to 4th. And actually the dip here, it can keep vanishing. If you have a higher quality device, it can keep vanishing going towards 0. And this is a very distinct behavior in this kind of system. And also we can show the phase diagram of this system. We found that at the very, very hot doping region like here, it actually deviates from the Luttinger-Liquid behavior, which I say Luttinger-Liquid behavior is the power law dependence. It deviates from the power dependence at the very, very low, hot rich region. And then near the charge neutrality, we can still get the power law down to 50 millikelvin. And this is the fine tune of such a system, and we can still maintain the Luttinger-Liquid physics. And if you keep doping it, it's going to be the isotropic area. So I want to give you a quick summarize. So for such a system, it actually shows a phase which has exceptional large impedance transport anisotropy. And this anisotropy can have a resistance ratio over to be 10 to 4. And the resistivity corresponding to this number is around 50. And the power law scale conductance along the hard direction, and which also shows a single alpha versus the temperature and external bias. And also this interesting zero bias dip behavior, it shows along the easy direction. And this is the characteristic of such a twisted Moiré tungsten dichloride at around 3 to 6 degrees, which we found so far. And the question, is there any connection to the sliding Luttinger decrease? And is this the real expansion from the one-dimensional Luttinger decrease to two-dimension? This is something that we are curious. And if it is, what should we expect? So the first thing that I think we should expect is that can we see spin track separation in two-dimensional situation? Is there any measurement method that we can try along this direction? For example, the tunneling measurement, which has been applied in the wide-dimensional situation. Or can we do some optical measurement to measure the spectroscopy of such a system? The second direction, which I think is very, very interesting and very, very excited about this direction, is that can we construct the quantum Hall effect based on such a two-dimensional anisotropy Luttinger decrease? And this actually has been pioneered by also our audience and our invited speaker this time. And also, I really appreciate Charlie for a lot of discussion along this direction. It's really exciting if we can construct such a one-dimensional Luttinger decrease. And if we apply magnetic field, it shifts the K-space a little bit. If we hybridize, can we create a new quantum Hall effect or the quantum oscillation based on such a non-Fermi decrease? That's a question, and that's also something that I'm really interested to investigate in the future. So let me quickly wrap it up. I want to say that the 2D material there is only a few been investigated, and we still have a lot of feminine that we haven't really looked into. And also, this is a lab that I want to explore in the future at UIUC. And I'm really excited to be here and really excited to start my new journey here together with everyone. Thank you.
If you take a bulk of the Delaware withdrawal,
Mm-hmm.
what's the size of the A and B?
So the bulk, I have no number, but for the monolayer from Dave Copland's result, they claim is around 3.
Okay, so it's,
yeah, that's what they claim. Yeah.
Essentially temperature.
I think there is very few temperature dependent, but you know the monolayer is very insulating, so most of their measurement is like 100 Kelvin something. Yeah. Yes.
One characteristic, if this is a magnetic metal
Mm-hmm.
is that it should have no resistance to shear.
Mm-hmm.
In other words, it would behave as a liquid solid.
I see. So you mean that if I can go to zero resistance?
Well, you know, the question is, can you ensure that ultimately there would be some resistance?
Mm-hmm.
it goes over the limit.
Mm-hmm. Mm-hmm.
But there may be some temperature range where it doesn't be very small.
That is what he saw. He saw
Yeah.
the resistance.
The
UV correction is like zero.
yeah.
No, I understand, but that's what he's saying.
It is.
Uh,
It's each wire is going independent of the other.
more of the loading.
And I actually have a comment,
Uh-huh.
which is that, that as you said, to get the sliding lecture liquid requires very fine tuning and a lot of optimism. It's much easier to get sliding phase if you have some of the modes on the wire gapped.
Mhm.
So you have some, we looked at a sliding Luttinger-Liquid, but I think you also have values. So
Mhm.
these are multi-component systems. If some of the degrees of freedom are gapped, it's much easier to get a sliding phase.
Mhm.
And looking at this picture,
Mhm.
it seems to me that thinking that something on the wire is gapped is not out of the question.
I see.
Then it wouldn't be a sliding lecture liquid, it would be a sliding, well, something else.
I see.
And that might also mean that if you went on a whole regime, you would get more interesting states than just the individual one.
I see. Thank you.
Yeah, so the fact that you get, all your exponents alpha equals approximately beta equals approximately 1, is this in line with the expectation that you're just kind of recovering the Fermi liquid damage?
No.
Not, so it's
Yeah, for me liquid it shouldn't be power law. Is that the question that you asked?
Yeah.
Yeah, for Fermi liquid it shouldn't be power law. Yeah.
The question is related, if does one understand sort of on what the alpha depends, you have sort of the one example with the twist angle, 3 degrees, the alpha was 1.5.
Yes.
Which does one have at least a quantitative understanding what was the reference alpha and then how it changed.
So that's a great question. So first of all, tuning the gating, we can really change the alpha a little bit. So this is what we show here in different angles. Yeah. And the second is that if you change the twist angle, you can definitely change the alpha. But the question here, we don't understand very well now is that, for example, for the 5 degree and 6 degree here, the sample we cannot really go down to millikelvin. The reason is because, as you can see here, the resistance already goes to a mega ohm. And for transport measurement, it's always the limit, there's some number at a mega ohm or like 10 mega ohm. And if we go lower, we cannot really reliably measure the resistance. So if we want to compare the alpha getting here and the alpha getting for 3 degrees, it's not easy because the alpha getting from 3 degrees is at a relatively like 2 order lower temperature. And so I'm not sure if it's fair to compare in this situation, but what it shows out is that in this situation, in this 5 degree, the power law behavior shows at a higher temperature. But for 3 degree, the power law behavior actually starts at around 500 millikelvin. So 5 degree, it shows around like 30 Kelvin. And then 3 degree, it shows around 500 millikelvin. So it's around 2 order lower, something like this. So there should be a phase diagram if you plot along the twist angle as well as the temperature. But we don't have a, like, we need to work more and fabricate more device and then conclude. Yeah, thank you. Yes, Tony?
You showed this graph of the IDP,
Mm-hmm.
which is very, at first sight, very like the idea that you get the secret stuff.
Uh-huh.
And if I understood you correct, you're rejected this was superconductivity by a fact that it was suppressed by a magnetic field. Sorry, it was not suppressed by a magnetic field.
Yes, yes.
But it's a triplet.
Yeah. Yeah. So in our situation, actually, we can measure along another orientation. And along another orientation, it didn't show the similar behavior. It shows the very, very high resistance. This is the first objection from the superconducting phase. Because for example, along the easy direction, it shows the superconducting-like behavior. But along the other orientation, so we just rotate the contact which we put on the device. We send the current across this geometry. The resistance goes very high. It then shows the superconducting-like behavior. And moreover, because if it's a triplet, it's completely different situation. But if it's like most of the superconductor which we have seen, we have applied up to 8 Tesla out-of-plane magnetic field, we still couldn't see this gap behavior getting killed. So we are not favor that this state is the superconductivity, but probably, I mean, if we apply higher field, what's going to happen, we have no idea, and we should definitely explore that.
Actually, if I remember correctly, the gap actually gets slightly bigger.
Yes, exactly.
Yeah, I think really nice discussion.
Thank you.